And welcome back to my channel Physics Lover. Today we discuss about the what is the Zeeman effects and its types, and we derive the interaction energy for the normal Zeeman effect. Before we going on the Zeeman effect, we must know the what is the Zeeman effect. And Zeeman effect is nothing. It is just a single spectral line split into many spectral lines in the presence of external magnetic field. That is, the Zeeman effect is a phenomenon of splitting of spectral line into the number of components with the application of magnetic field. And the Zeeman effect can be categorized into the two parts on the basis of the applied magnetic field. These are the normal Zeeman effect and the anomalous Zeeman effect. And the normal Zeeman effect is the spectral line split into the three components in the presence of a strong magnetic field. This is called the normal Zeeman effect. And the in case of normal Zeeman effect, spin quantum number is 0. That is the S equals to 0. In case of the anomalous Zeeman effect, the spectral line is split into the more than three components. These are unequal space line when we observe in a direction perpendicular to the weak magnetic field. In presence of the weak magnetic field, we only observe the anomalous Zeeman effect. And let's show the spin quantum number is not a zero, and we discuss with the help of the diagram. This is the splitting of the spectral line. This is the hydrogen atom in the magnetic field is off, and this is the sodium line. This is the line D1, this is line D2, this is line D1 with the wavelength 5890 angstrom, and this is D2 is 5896 angstrom. In case of the normal Zeeman effect, the when we apply the external magnetic field, the single spectral line is split into the three lines. In the sodium line D2 and D1, this is the single line is split into the four lines. And this is the D2 line with the wavelength is 596 angstrom, which is split into the three lines. That is, the in case of the anomalous Zeeman effect, a single line is split into the more than three lines. There is four lines, there is six lines. And in case of the normal Zeeman effect, the single line is split into the three lines if we applied the magnetic field. And let's go on the interaction energy for the normal Zeeman effect. Normal Zeeman effect, as we know, we take the hydrogen atom as like before and place in an external magnetic field in a z direction. Due to this, the energy level of atom changes. That is, the energy level are shifted from the lower to higher. And the Hamiltonian of the system for a single electron in the presence of external magnetic field, we can be write as the S naught equals to H equals to S naught plus S1 and the E phi, where S naught is the unperturbed Hamiltonian and H1 is the perturbed Hamiltonian. This is the our potential energy for the external magnetic field applied on the single electron. And then, since the presence of external magnetic field, B, the Hamiltonian of charged particle can be written as this is the Hamiltonian H equals to P square by twice m, but here is a P minus E by C times vector A whole square divided by 2 pi, and this is the potential energy. After then, this is the P square by twice mu E phi minus E by twice mu C A dot P P dot A. This is the vector sign, vector A dot P and plus vector P dot vector A plus EA square by twice mu C square. This is, let's say this is equation 2. After then, comparing the equations 1 and 2, we get this expression h1 is equals to minus c by twice mu c, and this plus, this is the equation 3. And this is the, as we know, this is the momentum operator. So momentum operator p equals to minus I r square delta. Then equation 3 becomes this. And the a dot p and the p dot a dot p and p dot a, this is the p dot a. Sorry for this, let me correct this. This is the p dot a, and we operate this, we get this term. From here, we can clearly show that from the Gauss divergence theorem, del dot A should be 0. And then, considering the first order approximation, then we can neglect this term. And the equation 4 become this. H1 equals to minus I r squared E by twice mu C, 2A the del equals to, this is equals to H1 is this, and this is the this, and 2 is cancelled over, and finally we get this expression where the p is minus I r squared delta. This is the momentum operator. Let's say this is the equation 5. After then, since as we know the a dot p equals to 1 by 2 b cross r dot p, from this we observe this, and the magnetic field in z direction, so that the 1 by 2 Lz and Vz. Let's say this equation 6. After then, from the equation 5 and 6, we can get this value h1 is equals to the E by twice mu c, and the this is the a dot p. This is the a dot p. We substitute the a dot p from the equation 6, we get this equation. Now, according to the perturbation theory, the first order change in energy can be written as the E n dash equals to psi 0 L and m h1 psi 0 n L m. And the substituting the values of h1 from this expression, we get the, this is the our expression. And here I use the orthonormalization condition, and we get this, and this is the orthonormalization condition. After then, simplifying this, we get this. Therefore, the a n dash equals to E bz by 2mc and the ml h cut. This is the E bz by twice mc is the omega L, and this is the required expression for the Zeeman shift. Also, E n dash equals to the E n0 plus EB by twice mu c ml h cut. This is equation line. This is the for the high energies, for the higher level energy. This is the E high is the E naught 0, and this is the plus sign. After then, the low energy case, we just flip the sign plus to the minus, and nothing is changes over here. This is our interaction energy for the normal Zeeman effect. Thank you. If you uh, satisfied with this video, please like, share, subscribe, and keep supporting my channel. Thank you.